Hello everyone and welcome back to our channel. In last video, that is video number 5, we covered operating system and CPU scheduling algorithms. Today in video 6, we will cover deadlocks and process synchronization. First topic is deadlocks. A deadlock happens when two or more processes are each waiting for a resource that another process in the group is holding and none of them can proceed. It's a permanent standstill. So here, process 1 is holding resource 1 and is waiting for resource 2. And process 2 is holding resource 2 and waiting for resource 1. So this has become a standstill situation. They are both waiting for a resource that another process is holding. And therefore, they will not be able to proceed. And that is why this is a deadlock. For a deadlock to occur, all four of these conditions must be true simultaneously. That means they should all be true together. IBPS often asks which of the following is not a necessary condition for deadlock. So you should know all four by name. The first condition is mutual exclusion. At least one resource must be held in a non-shareable mode. In simple terms, only one process can use that resource at a time. If another process requests that resource, it must wait until the resource is released. So this is mutual exclusion. Second is hold and wait. A process is holding at least one resource while simultaneously waiting to acquire additional resource held by other processes. The example that we discussed. Here process 1 was holding R1 but was waiting for R2. And similarly, process 2 was holding R2 and waiting for R1. So this is hold and wait. Third is no preemption. A resource cannot be forcibly taken away from a process. It can only be released voluntarily by the process holding it. So that means operating system cannot intervene to give the resource to other process. It can only be released voluntarily by the process holding it. So this condition is no preemption. Fourth is circular wait. Closed chain of process exists where each process is waiting for a resource held by the next process in the chain. So for example, process P0 is waiting for a resource held by P1. P1 is waiting for a resource held by P2. P2 is waiting for a resource held by P3 and so on. So here a closed chain of processes exists. So this is circular wait. Now all four conditions must hold true together. Removing even one of these conditions is enough to prevent deadlock. So all of these four conditions must be true simultaneously for a deadlock to happen. There are three broad strategies for dealing with deadlocks. First is deadlock prevention. Design the system so that at least one of the four necessary conditions can never occur. What are the four necessary conditions? These four. So you have to design the system in such a manner that at least one of the four necessary conditions never occur. Example is eliminate hold and wait by requiring a process to request all resources it needs at once upfront. So, if a process requests all the resources it need at once, it will not have to wait for any other resource, and thus we have successfully eliminated hold and wait and deadlock will not happen. So this is the first approach to handle deadlocks. Second is deadlock avoidance. The system allows the condition to exist, the four conditions that we have discussed, but it carefully analyzes each resource request before granting it to ensure the system remains in a safe state. What is a safe state? It is a state where every process can still complete under the worst case scenario. Classic example, Banker's algorithm, very important. So in Banker's algorithm, it first requires every process to declare its maximum resources need upfront. So every process will have to declare how many resources it needs at first only. And then secondly, it checks whether granting a resource request keeps the system in a safe state before actually allocating it. So first it will check how many resources are needed by a process, and then before granting a resource to that process, it will check whether the system will be in a safe state or not. So this is Banker's algorithm and it is an example of deadlock avoidance. Very important. Third is deadlock detection and recovery. The system allows deadlocks to potentially occur, but periodically checks for them and recovers if one is found. Example, by terminating a process or forcibly taking back a resource. So here, the system does not place restrictions on resource request and makes no safety checks upfront. Instead, it allows deadlock to happen. Periodically run a detection algorithm to identify cycles and then take action to break the deadlock. So remember, it takes a action after a deadlock has already occurred. So this is the third strategy, deadlock detection and recovery. Now, resource allocation graph. A resource allocation graph is a directed graph used by an operating system to keep track of state allocation, specifically which process hold which resources and which processes are waiting for other resources. It is primarily used for deadlock detection and deadlock avoidance. A graph consists of vertices, that is nodes, and edges, that is connections. First, vertices or nodes. Processes are represented as circles. Example, P1 and P2 are processes and they are represented by circles. These processes are active programs requesting or holding resources. Then resources are represented as rectangles. Example, R1, R2, R3. Inside each rectangle, dots or inner boxes represent individual units or instances of that resource. Example, so here one instance of resource 1 is available. Resource 2 also one instance is available. But for resource 3, two instances are available. Second, edges or arrows. Request edges. If an arrow is pointing from a process to a resource, that means the process is currently waiting for that resource. So here an arrow is pointing from P2 to R2. That means P2 is waiting for R2 and also P1 is waiting for R1. Assignment edge. If an arrow is pointing from a resource to a process, that means the resource has been allocated to that process. So here this arrow is pointing from R1 to P2. That means P2 is holding R1. And also this arrow is pointing from R3 to P2. That means P2 is also holding R3. And similarly P1 is holding R2. So remember, request edges from a process to a resource. That means the process wants that resource. It is waiting for that resource. And assignment edge is from a resource to a process. If an arrow is pointing from a resource to a process, that means that process is holding that resource. So I hope this is clear. Single instance versus multi-instance RAG. Visual representation. In single instance, only one dot inside each resource box. In multi-instance, multiple dots inside resource boxes. So here, R3 had two instances. There were two dots. So that is why this was a multi-instance RAG. If R3 wouldn't have been here, this diagram, including P1, P2, R1, R2, would have been a single instance RAG. Is a cycle a deadlock? In single instance, yes, always. A cycle guarantees a deadlock. In multi-instance, not necessarily. A cycle is a necessary condition, but not a sufficient one. Detection method. For single instance, simple cycle detection algorithms. For multi-instance, Banker's algorithm or deadlock detection matrix. Second topic is process synchronization. When multiple processes access shared data at the same time, things can go wrong if they are not properly coordinated. Process synchronization is used by operating system to coordinate execution of concurrent processes so that they do not interfere with each other, ensuring data consistency and order of execution. The race condition. A race condition occurs when two or more processes access and modify shared data concurrently, and the final result depends on the unpredictable timing or order in which their execution steps happen to run. This produces inconsistent or incorrect results. So, here is the example. Imagine a shared bank account with a balance of rupees 1000. Now, process 1 wants to deposit rupees 500. It reads balance as rupees 1000. Process 2 wants to withdraw rupees 200. It treats balance as rupees 1000 before process 1 writes back. So now process 1 writes rupees 1000 plus rupees 500, which is rupees 1500. Process 2 writes rupees 1000 minus rupees 200, which is rupees 800. It has overwritten process 1 work. Result: the deposit is lost because final balance becomes rupees 800 instead of rupees 1300. The critical section problem. The critical section is part of a process's code where it accesses shared resources or data. For example, we saw here two processes trying to update the same bank account simultaneously. Therefore, it led to incorrect results as the access was not controlled. The process that uses a critical section has four parts. First is entry section. The process requests permission to enter critical section. Second is the critical section, where the process accesses or modifies shared resources. Third is exit section. The process releases the resource so others can use it. Fourth is remainder section, the rest of the program that does not use shared resources. The solution to critical section problem must satisfy three conditions. First is mutual exclusion. Only one process can be inside critical section at any given time. Second, progress. If no process is in the critical section, the decision of which waiting process enters next should not be postponed indefinitely. It ensures that waiting processes eventually get a chance. Third, bounded waiting. There must be a limit on how many times other processes can enter the critical section after a process has requested entry. It prevents starvation. Remember starvation? In CPU scheduling, we have seen starvation for short job first. If shorter running processes keep on arriving, the longer running process will have to wait. So, therefore, here also there must be a limit on how many times other processes can enter the critical section after a process has requested entry. Mutex. A mutex or mutual exclusion lock is a synchronization mechanism which ensures that only one process or thread can access a shared resource or critical section at a time. It is basically used by operating systems to manage access to shared resources and prevent race conditions. A mutex acts like a lock with two states, locked and unlocked. How it works? First, a thread requests the mutex or lock. If the mutex is already locked, the thread waits. If the mutex is free, it is granted and the thread enters the critical section. A thread that locks a mutex becomes its owner. Only that specific owner thread is allowed to unlock it. After completing its work, the thread releases the mutex, which is unlocked state. Another waiting thread can then acquire the mutex. Semaphore is another synchronization mechanism. The first one we have seen was mutex. It is essentially an integer variable used to control access to shared resources by multiple processes, preventing race conditions. Two operations are performed on a semaphore. First is wait operation, denoted by P. It decreases the semaphore value. If it goes negative, the process is blocked. Second is signal, often denoted by V. What it does, it increases the semaphore value, potentially unblocking a waiting process. Now let's understand this with a very simple example. Imagine a car parking lot with three parking spaces. Outside the parking lot, there is a sign S which initially shows 3. This sign represents the semaphore value. The first car arrives. The wait operation is executed, so S decreases from 3 to 2. Since a parking space is available, the car enters and parks. Next, the second car arrives. Again, the wait operation executes, reducing S from 2 to 1. The car also parks successfully. Then, the third car arrives. The wait operation reduces S from 1 to 0. The last available parking space is occupied. At this point, the parking lot is full because S is equals to 0. Now, a fourth car arrives. The wait operation is executed once again. So, the semaphore value becomes -1. Since no parking space is available, the fourth car cannot enter the parking lot. Instead, it is blocked and must wait until another car leaves and frees up a parking space. There are two types of semaphore. First is binary semaphore. The integer value is only 0 or 1. It acts similarly to a mutex, but unlike a mutex, any process can signal or release it. It lacks thread ownership. Remember, in a mutex, a thread that locks a mutex become its owner. Only that specific owner thread is allowed to unlock it. It does not happen in semaphore. Any process can signal it or release it. Signal operation means release. Second is counting semaphore. The integer value can range over a larger set of integers, used when multiple instances of a resource exist. It is initialized to n, that is total number of available instances of a shared resource. As process consume resources, they call wait, and as they free resources, they call signal, like we saw in the example. So that was all for today's video. In today's video, we covered some important and fundamental topics of operating system. In next video, we will cover memory management and disk scheduling. If you gained some insight, do give us a like. If you have any queries, do let me know in comment section. And if you still haven't subscribed the channel, please do it so that you do not miss any important videos. Thank you so much and keep watching Array.